report on this. Okay, great. So IT today took just miraculously little time. So, hi everyone, and welcome to our first back seminar in 2024. I mean, I really enjoyed this opportunity, to say Happy New Year to everyone. So,
Happy New Year too.
it's spring tomorrow, right? So, today we have a star guest. Jeffrey Shragge, a professor from Colorado School of Mines, one of the leads for a very famous consortium.
Center for Wayfin.
So, and yeah, I'm really pleased to see Jeff today. So we go back what 9, 10 years when we met first time in Perth when I was still at Curtin University and Jeff was finishing his postdoc and maybe you became already an assistant professor at University of Western Australia. But he started with his Bachelor of Science at Queen's University in Canada, then Masters in University of British Columbia, many years of PhD at Stanford in seismology. So now professorship, as I mentioned. So Jeff can wear many hats. So he has a lot of interests. Shallow geophysics for archaeology. I remember you searching for these shipwrecks, right? On Australian, on Australian coast and many other things, including high performance computing, including seismic imaging algorithms. And today we have a really cool topic, and the floor is yours. So can you please introduce the topic?
Yes, thank you, Stas. Hello, everyone in the room. Hello, everyone online. Thanks for the introduction. I happen to be. Got it. I happen to be on sabbatical right now over at Stanford, and I'm here for the winter quarter and took the opportunity to come across the bay and visit with you all for a chat and a beverage. So thanks for the invite. This work is a collaboration between myself and my research associate, Aaron Gerard, who actually was my PhD student in Perth, who came with me back to Mines. He's actually from Denver, so he was a visiting international domestic student, which was a rather confusing situation. But this project is really kind of an amalgam of two projects, which one involved people from ExxonMobil, and so you might recognize Bjorn Olufsen, and then also the second part is from Shell and TGS, and that's where Mike, Simon, and Karsten are from. And what we've been looking at is low frequency ambient wave field seismology on large nodal arrays. And I'll kind of go through that in the first few slides, setting up the motivation for why we're interested in this. But just so we're all on the same page in the data that's actually being acquired, here's sort of a very cartoon-like idea of what goes on in these types of ocean bottom node or OBN experiments. So you first have a remote operated vehicle that goes out and deploys all these nodal instruments on the seafloor. After doing that, then you have one or more source vessels that come set up large air gun explosions on a Zamboni-like pattern as it goes up and around the entire array. All the nodes are continuously recording, and then once you've done all your surveys, then you go pick up your nodes. So pretty straightforward. However, these are very complex logistics operations. And just give you an idea here, sort of a Fairfield nodal instrument kind of stacked apart. And in this case, we have two sets of sensors that are important. We have the hydrophone, which records pressure in the water. And then we have a 3-component geophone, which is in the land on the sea bottom. And sort of the typical recording range for these is 4 to 14 hertz, which I realize I have blocked that over there. Just give you the idea of what we're looking at there. So this is sort of not the recording range. That's the cutoff of the actual sensor. And what we're interested in is how far below that can we actually go. Now, to give you an idea on the dimensions and sort of the types of arrays that we're looking at, this is the second array that we'll look at the results from today, and this is the amendment array. We have the tip of Louisiana, so the Mississippi Delta is coming right out here. into the Mississippi Canyon. And right in here is that block that we're looking at. And this array is actually a 40 kilometer by 80 kilometers squared size of patch of the Gulf of Mexico seafloor. And there's over 2,700 nodes that have been deployed at an average sort of 1 kilometer spacing and a staggered grid on that, on the seafloor. And to give you an idea of what that sort of looks like for you in the Bay Area, this is the type of, the area that we're actually looking at. So I'm sure you've all sat in traffic going north to south, the 80 kilometers there. And just it's interesting to think about the logistics of trying to deploy an instrument every square kilometer in that array. So it's a very big undertaking. 1 square kilometer, yeah, which is a little bit larger than some of the other OBNs, which were a little bit tighter. Oh. So, yeah. Mm-hmm. Yep. It's pretty. I think the deployment is pretty straightforward, and I think you can have a few metrics that you can use to sort of determine those. You can look at how well they're deployed from their gimbals, their axis, see how well to vertical they are. In general, it's fairly low angle ground that they're actually put on. They kind of get settled down into the muck. So they're actually fairly straightforward to deploy. This was the actual deployment. Yeah. So the question is this the actual map, or is this the deployment, or the plan? This is the actual deployment pattern. And a few of those 3 holes were just things that I think were lost. They didn't quite float up to the surface. So I think a few nodes out of 2,700 were lost in part of this operation. Yeah. So how do we think about using this? Oh. You might have it somewhere. So these would be out for about 80 days in total is when they would be out. And then there might be about a 40 to 50 day period when all of them are recording simultaneously. They start deploying them, I guess, and then, as they finish it, there's that window where it's open and they start deploying them up at the end. So we have these continuous data, and the idea for what we normally use these for we want to use things like reverse time migration to do high resolution imaging. And so in order to do this, first we have to do a bunch of data pre-processing, which normally involves windowing out the shot intervals and throwing away the rest of the data. That's just not active shot time. From that information, we can go through classical kind of model building techniques, which involves a lot of iterative human intervention, increasingly sort of computerized now these days. But we want to build those initial velocity models that we can then use these as starting points for full waveform inversion. So full waveform inversion is the high-end type of model building technique that allows us to try and match wiggle to wiggle ideally. And in doing so, allows you to have the highest resolution estimate of your model. So there might be a few internal iterations of this, and then you say, okay, given where we're at, let's now do kind of a lower frequency reverse time migration, do an imaging in 3D volume, see how are we doing? And then you assess how we converged. And if not, then you enter back into the cycle. You might do a few more iterations of FWI, push the frequencies higher, and as you work towards convergence, and then eventually you do sort of the high frequency RTM. Hey, look, it's going to be spectacular. And in general, yes, you can have spectacular results. This is from TGS. Again, I'm blocking the logo down there, but this is an overlay of 2 things. One, sort of the blackened or the grayscale image, that's the seismic image. And then the color is the velocity model. So they're superimposed on top of each other. And just for scale, this one here is 40 kilometers in lateral extent and 15 kilometers roughly in depth. So a very large volume that you can see. Sort of the purples, blues, greens, that's getting faster and faster. Yellows and down to the pink, which are your fastest velocities. And the yellows, you can see that there's a lot of sort of shallow yellow. These are these salt bodies that are found all throughout the Gulf of Mexico. So it's sort of low density, so it's buoyant. It comes up and makes these really complex structures that need to be handled with great care. So the question is it the OBN data? And yes, this was the OBN data that they used for this particular project. It's the active source component of the OBN data.
So, and they were able to do such a beautiful image even in the shallow sea, or we don't see the plant.
Yep. Yep. It says cut off at 1 kilometer.
Oh, it's
1 kilometer depth. So yeah. Yeah.
Oh.
Yeah. So the 1 kilometer. Yeah. 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 But of course, it's not always going to be straightforward and easy. There are a lot of doing surveys like this. There's a lot of economic challenges in terms of the cost of running these, personnel time, the time needed to do all the data massaging to actually get into FWY to ensure that's going to work. We're not really talking about that today, but thinking more on the technical side of things. And it's really what happens when you aren't able to build a sufficient initial model that allows you to do, to converge your FWY. That's one. Or let's say you want to cut costs significantly by trying to reduce the time it takes to build these initial models. So what are some of the technical limitations on why we might not be able to do that? Well, here's a typical shot gather and air gun spectrum associated with a shot like that. And I think what's really interesting is that you look down here and there's a very fast roll off at the low end. And that's really sort of sub 2 hertz. There's a real lack of frequencies, which is just because it's really difficult to move the volume of water that you need in order to get those low frequency responses. Air guns just can't do it, even large arrays of them. And so what we're asking in this chat here is what information is available in sub 2 hertz OBN recordings if you decide not to just throw out all the information in between the shots, but to consider it all together, sort of like a continuous record. And so that's what we're going to be looking at today. And in terms of the agenda, there's 4 items that we're talking about. So why are we interested in low frequency ambient data? How do we extract it? Is it sensitive to subsurface structure? And what wave phenomena are we actually seeing in these low frequency wave fields? So let's move on to why are we looking at this? So I've gotten creative with PowerPointing here and sort of been able to go from a situation like this to a situation like this, where now we don't have any of the boats. We just have those kind of deployed on the subsurface, but let's say there's energy bouncing around in the subsurface. And so we might have a question, well, you have a seafloor looks like this, you have an OBN-A. Well, what type of information is going to come in at A if you're not doing active source? And in fact, the oceanography community has been looking at this for decades, and they know very well that there's a lot of energy that comes in. So the ambient wave field community, that's sort of the 1 hertz down to 0.001 hertz. There's a lot of ordinary wave energy that you start having winds interacting, getting waves going. There's actually a pressure disturbance that transmits all the way down to the ocean floor that sets up surface waves that propagate. And it's a wide variety of a wide band of information there. As you can see that the lower red line there, is a pretty big hump right there and there. So this suggests that there could be a lot of interesting information available to actually think about using. So down the infragravity waves, sort of down here. I'm not exactly sure of the mechanisms that generate them.
6-second one is a real bother for observation. That is not as well as the coast. So
yep.
So I wondered how you imagine that
yeah, that well, when surface waves are probably going more horizontal, so surface waves will play strongly into this this talk. And this is just an example of now moving to actual measurement. So the 2 black lines that we have there are from sort of Peterson's groundbreaking. He was with USGS. He did a study of the background noise levels all throughout the world. And the top line is sort of the high level. The lower line is the lower level. And if you think about that band, it's sort of, as it's been explained to me, sort of 95% of the time, you expect to have 95% of the energy kind of falling within that band. And what we have here, the other colored lines, this is actually from a station in northern Siberia, just outside of Novosibirsk. And what you see is that in the winter months, January, April, we have a much lower level. But as you get into the brief period where the seas are actually open, there's a lot more energy storm action going around, a lot more energy rattling around. So clearly, sir, we're actually measuring some of these things, this information. And so what I'm very interested in is we have this type of spectra, and we have our active source frequencies, which kind of fall off right there. And then we have our ambient wave field. And what I'm very interested in is, can the ambient wave field frequencies kind of be a bandwidth extension that allow us to do some interesting things with some of the tools we already have developed? So that's what this talk is going to be largely focused on. So let's now look at some of the array data that we have. So this is the first array that we worked on. This is from the Gulf of Mexico, an Exxon data set. And this was published in Geophysics last year. And we're going to look at a spectrogram from that red star location. So we go in here and we start seeing for 30 straight hours, we can do sort of 2-minute windows. We do look at the spectrum from that, do the next 2-minute windows, and just stack them up horizontally. So what we're looking at here is sort of a calendar time, how the frequency structure changes. So what types of things do you see in that array, or in that image? Like these things in here? Yeah. So those are interesting. Those are actually, there was active shooting in that time, and that's when the boat was going over it, turning around, going back and forth. So that's the low frequency component of active shooting. What else do you? Okay, so I think you're probably referring to over here, the kind of the white patch. Yeah, that's there's a storm energy that happened in the Gulf that time. So that louder information there. What else do you see? Yeah, so that's sort of there, and it clearly cuts off in the low frequencies, and that's because someone decided in some hardware setting to put a low cut filter at 0.3 hertz, much to our dismay. The other thing that's kind of interesting is there's this line at 2 hertz, which it turns out that there is a light on board that twice, 2 times a second, it turns on and off, and that electromechanical signal it's really, really weak in any particular period. But if you start stacking it over minutes, then it actually it's stationary and it dominates at that frequency. So an interesting observation. The light on the node flicking on and off. Yeah. It could, yeah, I'm not sure if it's. These are the geophones, the 3-component geophone with the pressure sensor over top, and then so the other recording hardware digitizer all within the same unit. So the low frequency response for these would be at about 4 hertz, sort of flat to 4 hertz, and then it tails off. 1/f. I think it's 1/f. And it's a little bit higher in that case, yeah. So and normally the pressure sensor data, it falls off. It's not as usable at lower frequencies compared to the geophone. We haven't tried it on this, and this is obviously beyond our university's ability to deploy such a thing. It was more of a convenient partnership. Well, let's wait till the talk unfolds and see what's actually in the data. That's why we're actually doing this experiment. Mm-hmm. Yeah. And then we go for beer. Ah, okay. Yeah, you didn't explain that. Yeah. Yeah. But this is the first one. We have another one, so don't you worry. All right. So here is.
Wait a second. So if we go back, these high frequencies, they are recorded. So I see. So basically, these are local.
Yeah. Well, in this case, we purposefully asked for them to only give us sampled at 8 hertz. So we didn't want to have any of the information. That allowed us to, first of all, it's a more manageable data volume to handle. And then there's other, let's say the technical risk from the companies seemed much lower if we didn't actually have any of the active shot. So they thought. Dun, dun, dun. Here's again that second survey that we're looking at. So we can repeat this experiment for the amendment, where in this case, hey, there was no low frequency cut applied. And this is now 66 hours, so almost 3 days. And again, sort of bands of high energy windows, but now we actually have like almost down to DC in terms of the energy that we have. So again, no instrument hardware cutoff, and these are kind of an interesting repeating waveform right there. It's it almost looks like it's it's about 0.05 hertz, and then it's a multiple integer multiples of that. And what's interesting, if you go back to your Fourier class, that where you get those types of things, that sort of discrete thing is where you have continuous repetitive signals, right? And so, well, let's see in the talk if we see anything that has about a 0.05 hertz or 20-second periodicity as we come in. Yes. Yeah. No. And in fact, not shown in here, but this array was actually recording when a hurricane went directly over top of the array. And so we're right now working on, there's a little bit of a different noise regime, as you might expect when you have a hurricane over top of an array versus sort of standard. We have anything from 600 meters down to 1.8, almost 2 kilometers. So a variety as you come off the shelf. Yeah. Okay, so we have some interesting data. So how can we actually extract this? And so if you have, one station, that's great, but if you have 2 stations, then you can start looking at correlations. What happens at A, how does that then reoccur at B? And so we're going to be using, seismic interferometry in order to do this. So waves that, let's say this is kind of the interface propagating at the seabed. If it hits A, then it goes to B. We can use that information in terms of the relative delay. And this goes back to classic seismic interferometry that we're now, in year 25 plus in terms of working on these types of things. And the idea is that you have some source that goes off, a wave packet comes to A, and then it goes to B. Well, guess what? If A is your stopwatch, you can, through correlations, be able to say, well, there's going to be a time lag from the trace recorded at A to the trace recorded at B. And through the power of correlation, you can actually recover what that delta T is. And, interferograms effectively do that. So the correlation of A with B, and that's how it's going to have maximum correlation at that delta T, which is the relative shift it takes, the time it takes to travel across. And the key association is that this is kind of like as if you had an explosive source going off at A and then travels to B. It's not quite, not exactly anything like that, but kinematically, definitely, it shares a lot of similarities. You can also have the opposite, where you have something on the other side hitting B and then going to A. And then in that case, you'd expect to have a negative correlation window if your reference frame was still A. Okay, so let's make it a little more complicated now. If you have many sources on one side, then you're going to stack all of those together. And by averaging that process, you're going to come something that hopefully gets towards what the Green's function would be in the system. You do it on the other side, and hopefully by stacking over many different events, you'll actually get a symmetric response, meaning that the travel time between A and B is the same. And if you average out to kind of the same waveform going from A to B as there is from B to A, you expect symmetry in the experiment. This is still very much just, yes. But I'll show you very quickly that now if we go here, now this is where we have not just A and B, but now we have many Bs that are spread out there. and you actually do this on field data, this is at this one array, this is the type of response that you would get. So here at A equals 0, you know, basically get the strongest autocorrelations as you'd expect. And then as you step out here, you start seeing these X-like, you know, arrivals, which in those cases, those are the surface waves that are traveling along the seafloor. And then you see some other exotic ones, such as in here, which are going to be some of the guided P waves that are faster that you have going on. So what we're going to be looking at here are these virtual shock gatherers, or VSGs. That's what we're going to call them. So, you know, it's great if we can actually recover them, but if they're not sensitive to anything, then what's their value? So let's do a kind of a sensitivity analysis. And in this case, we're going to go back to this array here where we have, again, this is the center point A, which is going to be the trace that's our reference trace. And we're going to correlate against all those in pink. So in this case, we have the inline direction going north-south. But of course, these are 4 components. So in this case, we have the pressure, we have the verticals, we have the inline component, and then we have the transverse component. We can look at all of those different components sort of auto-correlated with themselves. We've done one, so the initial one here is now we're assuming they're all north-south oriented. You have to do a geometric, yeah. And we'll actually come to in 3D, of course, then you have to think about how to do that. So we'll show that in just a second. All right, so here is a VSG. For the first one is the P component, and the other one there is the Z component. And here we're seeing, you know, P waves, which is not unexpected to see that on the pressure component. But what's interesting is on that right-hand side, we're starting to see Schulte waves. And for those of you who don't know sort of the physics of waves propagating between a fluid and a solid, sort of in the 40s, Schulte, his equation, that basically there are three roots in it. So there's actually 8 possible solutions to this to wave phenomena at the interface. In the Schulte waves, this is going to be one of the slowest ones that actually propagates. And in this case, as you can see, it over 30 seconds, it propagates that 10 kilometers. So a very slow wave mode. And this is a mode that propagates, again, along the surface. So it's going to be expanding outwards cylindrically. It's going to be decaying into the ground, below the seabed, but also decaying into the water. And it's not actually decaying in the direction of propagation. The loss vector is, you know, up down in terms of what that does. Yes. This is perhaps the most surprise. So the question is, can you correlate, say, the vertical component Z with P? So yes, you can do that in principle. What we're showing here is sort of P autocorrelated with P. So we're only doing PP, ZZ, VV, horizontals, inline, crossline. So we're only doing sort of auto component correlations. The second part of your question, though, is I thought you're saying, so there's the frequency roll-off of the instruments. How can you actually correlate it when it's so far below the frequencies that you expect? Something along those lines, right?
Yeah, because between vertical and
No, this is just vertical with vertical. Yeah. So yeah. Okay. So then we have these other horizontal components. So this is now the second one is the inline component. And then the other one is the crossline component, which is the one that's oriented sort of orthogonal to the direction of propagation. And so we've interpreted these as higher order Schulte modes. And then there's also love waves on that transverse component. And we put the blue line there to show that there is a difference in arrival time between those 2 modes. Okay, so we're seeing a wide variety of wave field behavior going on at the subsurface. Yeah, similar, but based on the orthogonality of the projection and the difference in wave speed. So we expect the love wave to be faster than the Schulte wave mode here.
And they said having the shorter wave seems to have the same travel time process.
Well, not quite. No, no, see, look where they arrived. I did this intentionally. It arrives here. And you go here, it actually arrives there. So it's a little bit faster. Potentially, in this, yeah, I'm not sure. Mhm. Yep. Yep. So anisotropy was a question. So anisotropy could be in here, but what's interesting is that there's a clear number of sort of wave modes arriving inline, but there's only a single one arriving transversely. So that's, circumstantial evidence, but I think what we'd really like to do is confirm this with forward modeling to sort of say, is it consistent with that?
So Schulte wave is not expected to
It's going to be within the plane of, yeah.
It's very shallow. The average rise of frequency on
Yeah, that's true. Although it is you have to think about, and I'll show the sensitivity curve in just a second. It's the depth weighted average for so it is not just the surface.
But that was talking about yeah, he's in the end.
Yeah.
Can I
Oh.
come back to my question? You now show Z on the right side versus the horizontal component. On the spectrum, on the frequency period, pretty much the same. And yet, I understand it correctly, the Z component in terms of power plus correlation of the pressure sense.
No, the Z comes out of the vertical component of the geophone. No, we have 3 component geophones and a pressure sensitive. Yeah. Yeah. All right, now getting back to the 3D aspect of it. So here we have the geocentric kind of component where everything's oriented north-south, but really we want to have a wave vector, so basically radial and transverse. So what I'll be showing you next is something that's in a radial frame. And here is a movie now of wave propagation. So just kind of set this up. Here we have the vertical component Z between 0.3 and 0.8 hertz. And I've now overlain the P wave velocity model, a slice of that. And this was given to us afterwards by Exxon. That was derived from active source imaging. So that's just an input for visualization.
Which depth?
At 0.7 kilometers below the seafloor.
So we expect to be sensitive.
Well, that's the question, isn't it? Good year. All right, so let's now take a look at this movie. Okay. Pause it there and kind of go back a little bit. So here, this is the salt boundary. And what's really interesting, and this is your Schulte wave coming in, that as soon as it hits the salt, it starts propagating faster. And what's also cool is that we're very close to tracing out the boundaries of that salt. So kind of go here, maybe just kind of go back and forth like this. You can see it there, then kind of going like that. There, going like that. Apologies if there's a lag online, but clearly there's a sensitivity of these surface waves to that salt structure 700 meters below.
Have your active source, and you are often velocity, will you be able to
So yeah, so it's basically, I think you're jumping to the end of a future talk. The question is, if you were really, what information is derivable from these low frequency wave fields? So I think what's here is that it's clearly, showing that there's a change, a significant change in velocity at that location there. So if we took out the background velocity, you probably should be able to, almost even sketch out where you would expect that salt water body to be. Of course, this is just the 2D plane, and salt bodies are three-dimensional objects. And so we also have to think about the depth expression of that.
How do I, so quick, so I want to make sure.
Mm.
How can you select all the windows? How do you get the visual slice?
So the Wakefield movie knows nothing of 0.7 kilometers, other than it's based on its frequency content between 0.3 and 0.8 hertz. That's going to be sensitive to a range of depths. Okay, so you're going to basically have a bulk sensitivity that's basically the integral over the sensitivity kernels at those frequencies, given the kind of velocities. So it turns out that I, in fact, pick them judiciously, such that in this case, if you go in and have your typical VS and VP for the Gulf of Mexico, you can then compute what your depth sensitivity curves would be for these frequencies. And let's say 0.5 hertz, that's kind of in the middle of that band. And in this case, you see the peak at, well, here's about 0.7 kilometers there, and your bulk of your sensitivity is about 500 meters below mudline, but then you're sensitive all the way down to 3 or 4 kilometers. So effectively, you're integrating that response. And that's why where people do surface wave inversion, they can use the fact that you have the depth varying sensitivity as a function of frequencies, that if you invert many frequencies, you can basically be sensitive to a wide range of depths, and you can recover a depth-dependent model from your frequency data. That would be one approach to doing it. So similar, yeah, but it has that similar sort of sensitivity as MTV. Just to demonstrate the.
All of those factors. So
yes.
If you don't have that Shragge, body is not vertical.
Yep. Oh yeah, there's going to be an interesting sensitivity for sure. Okay, so hopefully I've convinced you that this is sensitive to the subsurface. And now we can start looking at results from this array, which again is 80 by 40 kilometers squared. And in this case, the movies that I'm going to show it sort of in that yellow box, tilted such that it's not north-south, but it's in a more logical orientation. And here's just an example of a vertical component from 0.3 to 0.65 hertz. And again, this is propagating, so the virtual source locations at 60 kilometers vertically, 20 kilometers horizontally, roughly. And what we're actually seeing is that we can have measurable propagation all the way the entire length of the array, so 60 kilometers. Okay, so that's a nice band. How low can we actually go? So now this is 0.08 to 0.28 hertz, and hopefully again showing you that it's propagating just as very similarly, but here you actually see more energy out in advance of the first movie that I showed there on the right. And that's because the lower frequencies are sensitive to greater depths, which generally means faster velocities, so they're propagating more rapidly.
Is it a square?
This should be plotted 1-to-1. That could be also that this is not a Green's function. You're also dependent on what wave field energy is actually coming into one to be measured at the other. So if it doesn't satisfy all of the interferometric principles, then you're going to have things deviated from sort of the exact response that you'd expect. And then we can even go, how about 10 millihertz to 80 millihertz? And sure enough, you can actually see propagation even at those really, really low frequencies. And what's really interesting is that these are about 3 orders of magnitude lower than the stated cutoff of the actual OBN instrument, which I'm not sure I've seen that reported before. And then we can also do fun things on the pressure component. And maybe as I'll have to let that play, maybe go back again and I'll see if I can here get this. So I want you to catch your eyes right in this area here. And hopefully you can see kind of a secondary scattering coming out of there, and we'll come back to that in just a second. All on the same scale, yeah. What scale do you mean? No, these have been, yeah, they're normal, yeah, yeah. So now we're looking at, on the right-hand side, note the different vertical axis, and now looking at these really low frequencies, and all of a sudden, these really low frequencies that we're getting in the wave field is actually sensitive down to 8, 10, 12 kilometers below mudline. And so it's interesting to think, if we can record this type of data, can this be used to build these large-scale, long wavelength velocity models that that are useful for elastic FWI STAS? That's a good question, because the question is it still Schulte at those low frequencies? And the global seismology community wouldn't even touch Schulte at these low periods. They would just say it's Rayleigh wave, right? So in this case, yeah. So in this case, Rayleigh or Love. So basically, the Schulte wave kind of asymptotes in towards Rayleigh, and basically that's because the wavelength is so long compared to the water depth, which then becomes inconsequential, effectively. Yeah. All right. So we can then say, well, let's now, instead of looking at 3D, I'm going to do an azimuthal stack. So now we're looking at absolute offset and time. And these are all these different frequency bands. And again, showing some interesting behavior. Probably the more interpretable ones are sort of here and here. But what's interesting is you're starting to see kind of a different character in there. It's starting to have like almost kind of slants that are stacked on echelon. That probably can see them a little bit better there. And so it looks like there's different wave modes that are contributing to these bands. And so we'll look at that in just a second. And then here's now the pressure component. And what we're seeing again is here a nice sort of linear move out, but then we're transitioning into a different structure in there. And to help better understand what those are, we can actually compute these velocity dispersion curves. So what we're looking at on the horizontal component is frequency, and then the vertical component is the phase velocity. So basically we're doing effectively slant stacking at a variety of different candidate move out velocities there. And what you're seeing here is that there's clear, two clear different wave modes that are contributing. There's been some discussion within our authors, but we're thinking this is sort of the Schulte wave component, then that goes into Rayleigh wave effectively. And then this one here, this is either part of the guided P wave field, or it could be a leaky Rayleigh mode. And leaky Rayleigh modes only happen when your effective shear wave velocity is faster than the fluid velocity that overlies that, which, if you have shallow salt, is at one setting where you could actually see where that actually happens. So there might be sort of something interesting there. We can go in here and, again, looking at those two things. So B is if you just band pass and look only in that sort of frequency band of B, we're seeing this behavior here. And then if you look at C, that's where we're seeing that kind of shingling like behavior there. So clearly different modes. Stas.
So another great question. So what the difference is if you look and those here on the left?
Oh, what's the periodicity?
Okay.
What's,
So
no, that's a question to you. What's the periodicity?
20 seconds.
20 seconds. Oh, look at this. Oh, that 20 seconds comes back in. Wait, I'll show you in just a second, okay? Here is then what we're looking for now on the pressure component. So again, we still see that sort of reverberations, periodicity 20 seconds, but hopefully now you can see here there's sort of a few different modes of guided P waves that are kind of bouncing around the subsurface there. And so this is a more typical of your guided P wave structure that you'd expect. These are not leaking, no. Yeah. Yeah, they're the ones that kind of do this and make multiple passes like that, multiple bounces. And these are sort of, yeah, at the ocean depth. All right, to get to Stas's question or an observation, the 20-second period. It's very interesting that we see this, but what's really kind of cool is that if you look at the active shot interval, and this is basically between successive shots on the actual instrument, on the shooting vessels, they're strongly peaked at 20 seconds. And what's really interesting then is the implication is that there's actually energy from the air gun arrays down to those low frequencies, which is almost heretical to say, but there was actually 2.4 million shots associated with this thing. So if you, that's even 1 million of them factor in, you take the square root of that, that's 1,000. So you're basically through stacking, you're enhancing your signal 1,000 times. So in any one sort of 10, 20-second window, you're not going to see that energy below the noise. But if you stack sort of the millions of shots together, then that actually becomes the dominant waveform. Yeah. Yeah. Over long periods, over long distances, right? Yeah. Okay, the last observation here is we looked at this type of thing, and this slide will fill in, but here's just one snapshot, and here's the kind of the primary wave field, and then we see the secondary scattering wave field. Well, you can do that for points all around this. So here is this location here, the crosshairs are the same as the crosshairs here. And I think clearly you can see all around that, there's these small circles within that. So that it's scattering from something. And what's really cool is that if you go into the active source model, and then right at that location, there's a salt pinnacle, a shallow pinnacle coming up that's actually a very effective scatterer of surface waves. And so right now we're working on 3D elastic time reverse imaging that will be able to actually image some of that shallow salt structure that's causing that scattering.
Not with the low frequency data. You don't do RTM of that.
We do RTM of that. TRI of that. And that actually will image, we've done some tests, you can actually image the shallow near vertical salt structures. All right, coming to an end here. So summary of key observations, hopefully convinced you that we can extract this sub 2 Hertz energy from long time recordings on these standard instruments. We see coherent energy down to 10 millihertz. It's sensitive to deep velocity structure, and we looked at a couple different structures. You know, there's the large contrast velocity interfaces. There's scattering from, you know, subvertical short wavelength velocity structure. It's likely the active source energy itself that's causing a lot of these reverberations sub 0.5 hertz. And you know, right now we're trying to figure out just what can we do with this in terms of model building? How can we use this information to create elastic models that would be really good inputs for FWI? And I think it would be kind of funny that all the effort that people have looked into building low frequency sources and trying to expand it on the bottom end, that maybe that energy's actually been in the ambient wave field the entire time had people looked there a little bit more carefully. So thank you all for your attention.
Thank you, Jeff. So
I'm surprised that the kind of the sort of there. We just reversed it.
So I need to think. Okay, I will ask this question, but first, I mean, thank you so much, Jeff. Usually, people online, would you like to ask any questions? Okay.
Hey, this is Tom. I can ask a question.
Tom Daly. Thank you, Tom.
Hi, Tom.
Hello. So just to go sort of back to the beginning of your talk and the actual instrumentation of the node. So the 3-component geophone is described as standard geophone. So it's like a resistor and or a coil and magnet geophone with a resistor in it. And so it has, I think, like a 3 dB per octave roll off on the low end.
Yep.
And you said that somewhere in the hardware there was a 0.5 hertz low pet
on this. Yeah, only on this data set. On the other one, they decided not to turn that feature on in the system.
Oh, okay. Well, that was nice of them for your work.
Yeah, we were very happy that they decided to do that. Yeah. So yeah, this is kind of a standard TGS. They would use that for. Yeah.
Okay, good. So, and then, so I would just say that I'm not surprised that you're able to see such low frequencies. It's just a matter of the noise floor, right? And the 3 dB per octave roll off. And, and like, I think it's really interesting what you showed with the 20-second period and the shot spacing. And so that actually makes sense that if you can have the signal to noise, you can stack that in and, as see it as you described. Yeah. Yeah. So, I'm,
Maybe to just kind of key into a little more explanation there. So you would have roll off in your magnitude, as well as there'd be sort of phase drift. You wouldn't have measure the true phase, but through the process of correlations, then actually some of those phase errors cancel because it's an e to the I, theta, e to the minus I theta.
right.
Those actually cancel. And so we were surprised that we actually could see well below that floor.
Well, the earthquake seismology guys will use the actual phase filtering estimate from the sensor itself, right, as a filter to apply. I don't know if you have that information or could do that or not too.
We could, but I think what's interesting is that it appears not to be needed for at least getting kind of like first pass coherence in your waveforms.
Because of the correlation.
Because of the correlation, yeah.
So you're doing a first order at least shift on the frequency phase spectrum, so you can get at least a straight line adjustment on it.
Yep, that's right.
Yeah. Okay, good. Yeah, okay, thanks. Well, I just wanted to check I understood all that. That was really, my question was really interesting to see the really low frequency stuff. It's nice in the 3D images show it with the wave field first in time shows it well. So thanks. It was a good presentation.
Thank you.
I think it was people by Rob Clay from Charles that did enough this symbolic waveforms. I'm not sure what's they show something very similar.
Was that the Long Beach experiment data that they had prior to that? Okay.
Yeah. Is this simply the fact that the energy source really long area, and that's where the wave field letters see primarily?
Well, I think what's interesting is that it looks like there's a variety of different modes, and what Aaron is actually looking at now is that we have within the 50-day record, we have the times when active shooting was going on, we have times when there was no active shooting, and then we have the hurricane time. So we have three different noise regimes, and he's now picking through to see what does it look like in those different settings to try and tease apart what really the active source contributions to that. Yeah.
The 22nd, that's really the square wave on.
It's so that's you have it's a source energy going on, like it's exploding, and then the boat travels and it waits 20 seconds. It sets off a explosion again. 20 seconds, it sets off, and so if you have basically one shot here, 20 seconds later, those are going to be highly correlated because it's a very repeatable event, and so you actually get if we only went to 60 seconds, but if you go to 300, 600 seconds, you'll probably see kind of that decaying every 20-second period. Yeah, exactly. And so you can model it like that, and that's why you're seeing the Fourier series-like behavior, right? Yeah, but it's not. It's going to be not going to have the coherent periodicity in time, and that's why we're like, what's going on? And then the idea was like, oh, maybe it's the shot interval, and then sure enough, it's the shot.
Two things. Orienting all these little boxes.
Yeah. Yeah. So that was the one bit of information we had from the active. We basically had their rotation tables. The gimbals, you can actually do a rotation based on the gimbal information, but it's a little bit more troublesome, and sort of knowing where your active shot location is, doing a bunch of them, it's a pretty straightforward least squares problem to figure out what the orientation of your geophones are.
correlation that's set by pretty good the details. You basically know which one source condition. But then you have which in the following three directions.
Yep.
You have to sort all of that.
Well, you just stack it all together. So if you think of what a 2D delta function is, right? You're trying to spatially localize, you kind of have to recreate at least a band limited version of what a 2D delta function would be, maybe in time as well. So that's what you're trying to recover. And that requires, energy from a bunch of sources outside of the array kind of coming in. So there's been a lot of theoretical work to say when does this actually work, but I think that in practice, it works much better than theory would tell us it should. It's kind of,
Every time that thing is posted up and set up the red, put on the radio. But that energy propagated it. And they came down and bird down. I'm surprised you're still going to have a compared loss. Theory, but those big microscopic
okay, well, yeah, so it's how that energy is partitioned at the seafloor. So you can get that, and yes, you can get body waves that then traverse along those paths, but then there's also a very efficient scatterer into Rayleigh wave modes. And so you can actually, those expand, or Rayleigh waves, Schulte waves, those expand cylindrically outwards. And that's why
It started very low.
Hey guys online, can you hear me on this laptop?
Yes, I can hear you.
Tom, did
Yes.
you? Okay.
yeah, and
I think
this floor,
so.
not in this
So
room, but in this floor.
what just happened? Jeff's laptop died, so we're talking without slides. I don't know. You did.
Yeah.
Power socket. The
Yeah, that maybe wasn't actually in. Yeah, so model building. Yeah, no, I think there are. That's the interesting thing is that that's falling directly into kind of what the global seismologies community has been doing for 30, 40 years. They build surface wave models. And I think what's really interesting now is we have an array that's of a size that's kind of in between the two communities, but it's a good opportunity to try and apply some of the kind of more global regional seismology in terms of their surface wave inversions on this. And that would be sort of the first stage that I would do before trying to do a full waveform inversion. It's let's just try and first choose the lowest frequency surface wave, which we understand a little bit better, and then we can think about the higher frequency.
So the real benefit for the exons and shells of this world is to build a much better glossy model. Is that the point?
It's
Raise better PhD students.
yeah, raise better. Well, that's the interesting question in terms of what is the value add for the companies. Ideally, if you can start pulling this data off right away when you bring the data in, start doing like an ambient wave field analysis beforehand, start building an elastic long wavelength model, then what the hope is then you would not need to go through as much pushing on the low ends of your FWI to try and get that bandwidth down to 2 hertz that you're more likely to converge in terms of the FWI process. So it's trying to bridge that gap, that the long wavelength velocity gap that hopefully can then use to bootstrap in for FWI. That's the goal.
If the goal is some sort of image, what would be the ideal frequency?
1 millisecond.
I guess that's the big deal.
basically.
That's the-
I mean, they all do very well with this stuff. Scattering all
Yeah.
your energy from these air guns, right? So
Yep.
This is getting you below the sun.
Oh, yeah, it's definitely getting below salt, but obviously they were getting below salt and
They were really nice.
they were really nice. Well, see, the other thing that they were doing, they had 80 kilometers in one, 40 kilometers in the other, and they actually did even 40 kilometers further offset shooting than the end of the array. So they were actually getting offsets to 120 kilometers, and they actually had sufficient separation that you would have your, air guns going off, you get the P wave coming in, but then you get the S wave converted at the bottom, and then that phase would come in, and there'd be sufficient separation that they could very clearly pick all the S wave arrivals and do tomography on the P wave as well as in the S wave. And that's just because they had those really, really long distances. So it was a bit of an experiment for them to do this type of array. But it worked out very nicely in terms of those really high resolution images. They were getting down to 15 kilometers, and that's down into the, you're down almost into the basement of the Gulf of Mexico at that point.
What are you gonna add to that? Pretty nice already.
Yeah. Well, it's, can we facilitate the starting of that? Or if we don't have to have that super off-end shooting, or maybe you don't need as many shots in the middle, I don't know. It's really
So there was
possible.
a term that Mike Kovich, the PM guy, also cited, and said that there was one to look at what was seafloor compliance. And there was a need to get low frequency information for seafloor compliance. I don't know what that's. Okay, so he said that for controlling their inversions, the DC term was called seafloor compliance, so. But you haven't come across that.
Not-
It just stuck with me because we think when they're doing the full waveform inversion, the really low frequencies are critical, and I know they have a lot of trouble getting those from the
Yep.
airplanes. And these, the state actually, that's that.
That's the whole point. Yeah, that's the whole point. Is it the bandwidth extension that they've, or is it an option for a bandwidth extension that they've been looking for, and it's already recorded in the data?
So part of that was in rotation versus translation, so it's, we're doing that, we wanted to get the rotation of the seafloor. I just was wondering, because now at these frequencies, you're down in rotation, because there's significant rotation of these stuff. You can solve it for rotation, and there's people that use the fiber optic.
Yep.
Gyro.
Yep.
Fiber optic gyros that they're trying to record, and I think once you get these frequencies, you may be able to get that numerically from your data.
Awesome.
Very nice. That's work.
So I know everyone wants to go. Jeff, I have a couple of questions as well. So first of all,
Here or at beer?
the Shragge wave.
Yep.
So that so you rattled this ambient noise, right? And through interferometry, you got the Shragge wave, but then basically you can use each sensor as a source, right?
Mhm.
So
So I showed
I-
one
I know,
VSG, but
I
there's,
know,
yeah,
I know.
27.
Do you know where the noise is coming from? Did you try to do any beamformer analysis, anything like that? So imagine you don't have a ship, a vessel. So my understanding is the vessel didn't contribute much,
It
right?
did.
Oh, actually, it's coming from
It's
the
the
vessel.
shot. It's the shots.
So it's not actually from the noise.
Well,
It's not the.
no, it's largely from the shots, and that's why we're doing where Aaron's next task is testing when we know there's active shooting, and then when there's not active shooting, and basically tease apart what is actual contribution from the air guns versus what is,
Or with the hurricane.
or the
But then,
hurricane.
but then,
What you do, it's just active.
So,
Well,
no,
it was all the data.
it was all the data. It was
Oh, that's what I'm-
not including the hurricane. We
So-
did, we snipped off the hurricane, so that's not in there, but
but if it's coming from the vessel, right? Then it's not this diffuse energy from everywhere, right? Did you need to modify, did you need to do any, okay, so it looks
Yep.
as
No,
nice.
they did do something, but he cut off the hurricane data. So-
Oh, yeah.
So he said they did have to do something.
Yeah, there was a little bit, yeah. And to be, I guess, I didn't go
So-
through the processing. There is,
So,
we do go through and we throw out the 30% noisiest windows because they're more likely to have more localized energy that would maybe record loud on one OBN, but not the others. So there's There's a pre-processing
Oh, fish
that
pump.
goes through this. Fish pumps, yeah, those are.
But did you try it without the vessel? Like,
Well, that's what Aaron's doing now, yeah.
okay.
We didn't
so-
realize until we actually got
so
through, we saw this periodicity, we're like, what's
what-
going on?
What I think would be interesting, you can get low frequencies, the 0.15 hertz,
Mhm.
right, from remote storms.
Mhm.
So you will have one direction, a storm from another direction. You can, illuminate from different angles. And also you can have like local sea winds, right? Did you look at any?
We've done all that,
floating
we've done
buoys?
beam forming, all that sort of stuff, yeah.
So on floating buoys, do you have anything like
So-
ocean wave monitoring?
Yes, so there's a couple ocean buoys that are out there. One of the TGS personnel is kind of pulling them right now and looking at.
Uh-huh.
And the other thing that we're looking to see is can we somehow say something interesting about the path of the storm based on the energy that we see? Because it came in, went over, and then kind of did that, so we can actually see that storm trajectory,
Yeah.
which is kind of cool. And it's a much different noise regime there. We see a lot more guided P wave energy that's going on in that.
Also very interesting.
Yeah.
Basically,
Yeah.
because storms aren't necessarily completely directed by what's happening in the atmosphere. They're also, the sea is a large component of what
Yep.
the storms normally do.
Yep.
Are you developing an early detection system?
For hurricanes, I think satellites will beat us every
No, but that's an NSF proposal right there.
Oh.
So, and
Folks at Boulder have done, they were shooting something
Mhm.
with the array at the ends of the radar.
Mhm.
They looked at all the storms and showed it, and they have a vector.
Yep.
It's directed, it's North Atlantic, Pacific, and that's.
Yep.
I can see, as you can see, a lot of signs when you have thousands of nodes in
Yeah.
kilometers apart that are all providing you a continuous stream of vital data.
Yeah.
Now make it 30 kilometers apart, not so good.
Well, and I think the other thing is that a kilometer worked here because we actually had fairly fast seafloor velocities. If you're shallow North Sea, you need to only be sort of 300 meters apart, otherwise you get, severe spatial aliasing. So it sort of depends on the seafloor
Yeah.
conditions and near seafloor conditions. So this was just a very nice data set, but then, yeah, you basically get to, but like what the astronomers have, right? You have a whole bunch of, instead of having one giant dish, you have now many distributed individual sensors that are great at detecting plane waves from space. And that's sort of what we have here. We have a very telescope of the Earth.
It's kind of cool. You can see all sorts of cool physics.
Yeah,
Who's not the-
this was TGS who acquired the data.
Okay, so when was it discollected?
2017, 2018.
So was there only one hurricane that came through?
There's only one hurricane at that time. Yeah,
in this city,
that went right over
Okay.
Coppin. Maybe there was others, distal to the array at that during that period, but.
Yeah. So another question, you didn't show any simulations. So how do you do RTM of WI without that?
Oh, so well, TRI was the one we're looking at,
Oh,
which is just,
TRI.
which is time reversal, which,
Okay.
the like in microseismic, right? You can do that. That's how we're thinking of that. But
That's a way.
yeah.
And
And then the other one is then how do you, if you're going to use this in like a full wave field sense, you have to be able to forward model.
that's my question. What
Yep.
do I need for that? How
So
high you need to
this-
capture the water?
Yeah, so this is something that the global seismology community has been actually doing for, about 5-6 years.
But not for the Schulte.
Not specifically for the Schulte waves, but the principles are the same. Is that you can basically say, here's my distribution of energy, and basically you model it from outside of the array to your virtual shot location. Then you take that energy that you record there, you then re-inject it into a second modeling, and you model to all your other receivers. And then you correlate those two wave fields just as you would do it in the Earth. And so there are ways that you can actually do this, and that's what one of the PhD students is actually working on now and coming up with. He's able to reproduce a lot of these things that we're seeing, like different wave modes. It's an interesting question. Where's the effective source depth? Many times when people are thinking about the ambient wave fields, they model it as surface waves on the bottom, but that didn't support the types of guided P waves that we're seeing, and we had to actually put the sources right up at the surface where the air guns were before we were able to actually reconstruct a lot of the observations that we're seeing. So there's a lot of interesting kind of source modeling physics that go in, they go in there that are requirement, a precursor to actually be able to use this for inversion.
Exciting. So I'm not gonna torture anyone. I'm ask more questions. So guys online, do you have any more questions? If not, then thank you for your time, and let's thank our speaker once again. Jeff, thank you.